The night sky is one of those things we generally do not expect change with, at least in our lifetimes. The clockwork motions of the sun and moon, the seemingly unshakable familiar state of the stars and constellations, is only really ever interrupted by the occasional comet or meteor, but sometimes it changes dramatically and without warning. In the year 1054, Chinese astronomers noted that a guest star had appeared in the sky, and they recorded it. This star was actually a supernova, and that ultimately formed the Crab Nebula, visible in small telescopes to this day. This could happen again. The prominent night sky star Betelgeuse in the constellation of Orion, noteworthy for its prominent orange color that can be seen with the naked eye, is among the closest stars to us that is expected to go supernova sometime within the next 100,000 years. It's very unlikely for this to happen within our lifetimes, but it will eventually do so. And as a reminder of how unstable and variable this star is, it has recently dipped in brightness by over a full visual magnitude. While it's probably not going to explode tomorrow, it does tell us that someday it will. My guest today is carefully watching this very variable star and documenting this period of unprecedented dimming of the star Betelgeuse.
Welcome to Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Edward Guinan. Dr. Guinan received his doctoral degree in astronomy from the University of Pennsylvania in 1970. He is a professor of astronomy and astrophysics at Villanova. Having been at Villanova for over 40 years, Dr. Guinan's work focuses on pulsating stars, binary star systems, the evolution of the Sun and solar-like stars, and the search for exoplanets.
Dr. Edward Guinan, welcome to the program.
Thank you.
Now, Doctor, one of your more recent things that you've been involved with is this dimming of the night sky, prominent night sky star Betelgeuse, which I'll bet most of my audience has looked up at Orion in the night sky and seen this thing many times. Now, what's going on here? How fast did this dim like this?
We've been studying the star for almost 40 years, and it's variable. Has pulsations, variations of 100 days, 5 years, 425 days. So these stars are unstable. They go out to almost the star goes out almost to Jupiter. So it's huge. And what they are is progenitors of a supernova, a core collapse supernova, where the iron core collapses and the star blows up. So we have a program, it includes more than Betelgeuse, but Betelgeuse is our brightest one, just to monitor these variations, to kind of probe what's going on in the atmospheres of these stars, not really to look for a supernova or anything like that. So this year, we were observing these for a long time. I do it with a colleague who does most of the observing. His name is Richard Wasatonic. He has his own telescope in his backyard, a little 10-inch telescope. And so whenever it's clear, he runs out and collects photometry. So this year, we're getting kind of tired of it. It wasn't doing anything extraordinary for a long time. It varies, but we've kind of figured out its variations. This year, we decided to do one more year, maybe to call it quits. And then it was acting normally, and then it would start to get fainter, which is not unusual in October, and then fainter and fainter. We said, it's probably going to stop, and behave like it did in the past. And then it just kept going. Each time I went out, I said, well, this is it now. It's near the bottom of its usual light variation. This is probably caused by a pulsation, but then it just went beyond anything it ever has done in the past, ever. Like all of recorded history going back to the 1830s. We couldn't find it being fainter than it is now. And in fact, it was observed last night from Philadelphia, and it's near 1.5 magnitudes. It's getting very close to Bellatrix, which is the star right across from it in Orion. So it's been exciting. It's been a whirlwind. I wrote a telegram in December, just recording. It was not meant for public. It was meant for astronomers, who to give them a heads up on collecting observations on bigger telescopes and different wavelength regions on the star, because it was unusually dim and cool. So that was the basis, and that got picked up, by National Geographic, and then it's been like in the news. And we had a follow-up. It's called Astronomer's Telegram. Follow-up on the 23rd of December. We're still getting fainter, and now I kept saying to myself, well, it's near the bottom. It's going to stop, and it hasn't. And still, I think it's part of a kind of a more significant kind of pulse than it usually has. But now I'm beginning to wonder, because it has behavior now that none of the other red supergiants have. I haven't seen anything like it. I still don't think it is a precursor of an explosion. You never know. I keep an eye on it. And I'm at a meeting in Hawaii, and I stepped out on the porch, the patio here, just to look at it last night, and it was really faint. I'm really looking for it. If the big exciting thing, if it got bright real fast, because that would be the signature of a supernova.
Now, it's worth noting here to the audience that 1.5 magnitudes, that is visually discernible.
Yeah.
You can go out and look at Betelgeuse, and it's dimmer than it normally is. So This is something you can go out and see with your naked eye. Now, you say that Betelgeuse is now in territory where it is behaving abnormally for even a variable star.
Yeah, it's outside the limits of what it's done before.
The question here is, the internet, after all of the media attention, the internet went wild saying, does this mean that Betelgeuse is about to go supernova? Now, we know that it's going to do that sometime within, relatively quickly in geologic timescales. But could this really be a precursor to a supernova, or is it just something that Betelgeuse probably has done in the past and will do in the future? Where are we at on that?
I wish I knew. I believe the later. I think it's not about to become a supernova in the next few days. It's predicted to go any time from now to about 100,000 years. So that gives you a wide window. And that's most of the supernova experts. I'm attending a meeting in the American Astronomical Society in Hawaii, and I've been talking to them, and they've been getting internet questions too. The consensus is that, first of all, no one knows what happens before. No one has ever observed a supernova before it blew up. They're usually too faint, and they're discovered when they're on the process of blowing up. So my feeling still is it's part of just an unusual episode of going on in the outer parts of the star. The star's convective. It's a big bubbling star, and it's just it's more bubbly or more expansive than it normally is. But then the supernova people who do theory don't really know. They think that it's varied. Most of them think there wouldn't be a connection until hours between the outside and the inside. It's 5 astronomicals away. The inside is like where the sun is, and the outside of the star, what we're seeing, is almost where Jupiter is. So they're pretty far apart. But one of the supernova experts, named Dr. Fuller, he thought in his models that it showed a dimming months before the explosion. But he's kind of an outlier in this. But most of them are not sure what happens, what the prelude, what the immediate event is, or light variations are before it blows up. So I keep looking at it. I'm not a theorist. I mean, I know the outside. I know how the outside of the star works, and this guy is just a bubbling. Has a big convective cells of hot material rising up and then subsiding, and it's not a symmetrical star. It has parts of it stick out from the others on the other sections, and it has ejected shells before. It has blown, not supernova, but it has ejected shells of gas that, if you put it in our solar system, would be out where Neptune is.
Is it possible that one of those shells is just occluding the star rather than anything going on with the star itself?
Well, there have to be research. Yes, that's another suggestion. Is that what's being done now is that there's it ejected matter and the matter has cooled, and it contains carbon and things like that. It's cooled, and the carbon has condensed into atomic carbon or carbon molecules, and is obscuring the star because of dust obscuration. We don't think that one's right, because we observe the star in 5 filters in the optical and near IR. And the V filter, the visual filter, is the one that you're seeing all the attention, because that's the one that everybody uses. But we have a filter set that measures its titanium oxide. It's a molecule that cool stars have. And the titanium oxide is a measure of temperature. And we're getting stronger titanium oxide bands, which indicate that the star has cooled about 100 or so degrees. And also, we think the star has gotten a little bigger. So we have other bands. We have other. We just don't use this B filter because it's messy. It's a messy area of the star spectrum. We have other filters, and the indication there is that I think that would kind of rule out a dust ejection, but who knows? So that's where we stand. We observed it last night. My colleague observed it last night in Philadelphia, and it was getting close to 1.5. 1.47 he got. And I was surprised at that. We thought it bottomed out. We keep thinking this is it. It won't go any lower. And then it surprises us. And next few nights it went down no more. So we're at a point where it's almost as bright, getting near the brightness of Bellatrix, one of the other stars that defines the rectangle, the trapezoid that Orion is. And if you look at Orion, Betelgeuse is normally rivaling Rigel, the foot or the knee of the star. They're usually about the same brightness, close to brightness. Rigel's a little brighter. Now it's just all you see is Rigel standing out. You don't see Betelgeuse standing out anymore as one of the brighter stars.
Let's imagine for a moment that it did go supernova. What would that look like from here?
That would be fantastic. First of all, what you would see is it would stop getting dimmer, and suddenly its brightness would go up. And in a couple of days, it would be brighter than Venus, -4 magnitude. And then it eventually, when it peaks 1 or 2 weeks into the explosion, it would reach the brightness, we think about on the magnitude scale, -10, which is close to the full moon. So it would, during that time, it would cast shadows. You could probably read. If you had good eyes, you could read by it. It would be like as if you had a full moon out. And that whole area of Orion would be just dominated by this brilliant beacon of blue light. And then it would start to fade months. It would start to fade back. And it would actually fade into oblivion. Like a year later, it would be really faint. And because what happens then, the dust shell blows off, and the gas shell blows off. And the core of the star, where the action is now, where the nuclear burning takes place, it's called iron. It's a core collapse. It forms iron. Iron is unstable, collapses. And then the most likely scenario, I heard people mention a black hole. The most likely scenario for this star's mass is a neutron star, or the other alternative is a black hole. It would just keep collapsing to a point. It's on the borderline of ending up as a black hole or a neutron star. Right on the border. Its mass is about 12 times the mass of the sun. And it ejects most of the materials, just eject it right into space. There'd be no danger. The things, Betelgeuse is 650, 700 light years away. So all this action, if it did blow up, took place 700 years ago. But there'd be no danger to us at all. It would just be spectacular to view it. It would be, and you could see it in the day if it were up. It would be that bright. It would be the brightest supernova. There have been naked eye supernovas in our own galaxy. This would be the brightest ever because this is the closest. So the other ones take place in 1054. We had a supernova. That's now the Crab Nebula that people could see in the daytime.
Yes. Now, I was going to ask about that. So in the aftermath, like with the Crab Nebula, you would have that expanding shell of gas forming a nebula, right?
Right, exactly.
And we would be able to watch that essentially in real time.
Yeah. This has been done in the last bright supernova was in the Large Magellanic Cloud in 1987. It's called supernova 1987A. It went up to 3rd magnitude, which is, it's a naked eye object. And that star has now been studied with Hubble and other telescopes. And what you see is the expansion. You see the explosive, the aftermath of the explosion, expanding gas, dust. And now they detected for the first time the remnant, which is a neutron star. But this is much brighter than that. But that's the last one. I saw that one. It was third magnitude, and I was very happy to see it. This would be out of the ballpark, and it would be, 1,000 times brighter than Venus. So this would really shine.
Now, that's actually kind of sad for me, because I think I was 13 years old at the time when that supernova happened in 1987, and I was like, I'm stuck in the northern hemisphere and I don't get to see it.
Yeah.
But it would be rather sad to lose Betelgeuse, though. That's one of the most prominent, stars in the night sky, mainly because you can see the orange color of the thing.
Yeah.
And it was also, as I recall, isn't Betelgeuse one of the very few stars that we've actually imaged the disk of?
Yes. Yeah. It's so big, being almost out to Jupiter, and near enough that it's imageable. It doesn't twinkle because it's almost has a diameter of, what they measured is milliarc seconds. It has a diameter of about 50 milliarc seconds. So it has been imaged. There's pictures of that on the web, and it has little bright and dark spots on it. And it's not symmetrical.
And those bright and dark spots make you wonder about that variability, right?
Yeah, we think that's part of it. Is that the theory is it pulsates, it's unstable, and you have these they're called supergranules, these giant blobs of hot gas convecting up. That makes it get bright, and then they cool off and subside, and a new one will come along. We have what we do with this, with the data that we have 25 years of continuous data using these 4 filters. We analyze it and then break it down into all of its periods, and it has several main periods, 5-6 years. It has the one that we think this is associated with. This is 420-day, which looks like a pulsation period. That's what we thought this was about, but it bottoms out around now. But not this deep. It has an amplitude of about 1/2 a magnitude, and this is now getting close to 1 magnitude. So we've never seen it an amplitude so bright, so strong.
Is there any indication of anything going on with Betelgeuse as far as exoplanets? I mean, could a star that's this violent and roiling even have them, or has there just never been any evidence of that?
No evidence. It would have swallowed them up if it had it. It would have been when it was very young, 9 million years ago, it would have been a B star, an early type B star or late O. So it would have a very brief time as a main sequence star. And brief, I merely mean brief, like under 1 million years before it expanded to become a red supergiant. So if there's planets there, they were long gone. They're swallowed up. They have been assimilated by the star. These stars live it's a massive star. The massive stars live a very short life. They have a spectacular life. They go out with a bang, but brilliant. That's where they're getting their energy. Their nuclear reaction rates are 100,000 times, producing 100,000 times more energy than the sun does. So they burn their nuclear fuel at a very, very fast rates, which means they don't live long. They die out. Someone asked me a question few days ago here. If you make the Earth, the sun's age, sun lives about 10 billion years. If you make that a year, like that, pretend that's these stars have lifetimes of days, weeks, on that kind of scale. So they're very rare, short-lived stars that go out with a splash. That's what will happen here someday.
And we have to take a break. When we come back, we're going to go into a discussion of one of I'd say probably the most intriguing type of star in the universe, at least for me, if you're looking at things like habitable zones, the Type K orange dwarf. We'll be back in a moment.
Be sure to like, subscribe, and share the video. And now, back to John.
And we're back with Edward Guinan. Now, Doctor, you also work with stars on the opposite end of the spectrum from Betelgeuse, really. These tiny, very long-lived stars, the red and orange dwarfs. And lately, red dwarfs have sort of fallen out of favor regarding their habitable zone because it's so close in and those stars are so violent early on, and there's just a lot of problems there. But Type K, which hasn't really gotten a lot of attention, it might be just right. Might even be better than our own star system as far as habitable zones. Can you go into what you've studied with these?
Yeah, was attending the American Astronomical Society meeting in Hawaii, and we gave a paper on this. It was called the Goldilocks star, K stars. So these stars are fall between properties of the G stars and the red dwarfs. And we studied both of these. We have two programs now. This two programs going. One called The Sun in Time, where we studied G stars of different ages, and really homed in on their X-ray and UV emissions. And then we did the same thing with M stars about 10 years ago, living with a red dwarf, we called that one, to study what their X-ray and UV properties and wind properties would be. And the reason is why X-ray, why UV? And it's because this kind of radiation it photodissociates. The ultraviolet radiation can break up, can break up water, H2O into H and into O. And the X-ray radiation will ionize it, so it strips away electrons. So that's what happens in our ionosphere. Ionosphere has ionized hydrogen and some oxygen. So that being said, it starts to dissociate the molecules and then ionizes them. And if there's no magnetic field, if the planet does not have a strong, this is our conclusion, no strong geomagnetic field, the winds of the star, which are plasma, sweep by and sweep away. It's called ion pickup. They sweep away these ionized hydrogen and oxygen, mainly hydrogen, from the planet's ionosphere. And eventually that erodes away all of the atmosphere of the planet. And this is especially important when stars are young. That's why we call these in time, the sun in time, or living with a red dwarf, is because when stars are young, they spin really fast. The sun, when it was young, and you can study those by looking at G stars in the Pleiades, which is 100 million years old. They spin like 2 or 3 day rotation periods. And this creates a very strong magnetic dynamo that produces coronal X-ray emission and ultraviolet emissions. The X-rays are 500 to 1,000 times the present sun, and the ultraviolet emissions are like 50 to 100 times because the stars are spinning so fast. During that time period, when that's the same period when planets are forming, they're being zapped by this high energy radiation. And if they don't have a magnetic field in place, that is going to be trouble, for the planet having water or even having an atmosphere. So our initial work was maybe it was like 20 years ago when we handed over our data on our Sun in Time project to people who model atmospheres. They modeled they applied the radiation. We had this radiation, X-rays, ultraviolet as a function of time, and they modeled for terrestrial planets in our solar system. And Venus didn't last very long at all before it lost its water because it's nearer. And Mercury had really, one of the theories is that Mercury is an iron planet, has a large iron core, but one of the collaborators believed that the winds of the sun may have been so strong and the X-rays and UV so strong that it even started to erode away the mantle of the planet. I don't know if there's other theories why Mercury has this large iron core, but one of the theories is that the sun's winds and X-ray and UV got even into the blowing away the surface. It's doing it now. There's pictures of Venus losing some of its surface. You see calcium and things like that still going on, very tiny amounts. So, and Mars, they modeled Mars. There's a paper out. The name is Helmut Lammer, who did the modeling work. We gave them the data and they modeled it. They came up with the theory that's still solid, that Mars in the beginning had Mars is first of all a smaller planet. It's 1/10 the mass of the sun. Their model was that Mars was once, because of all the geological features, once had water and oceans and a climate like our own, possibly even life in the first billion and a half years. And what happened is that it had magnetic field. And what happened is that the core cooled and solidified, froze out. And it opened, even though the sun wasn't as strong as it was when it was younger, it still was enough to ionize or dissociate the water, ionize it, and then the winds of the sun picked up those gases and blew them off. So the greenhouse effect on Mars at that time was mostly CO2 and water vapor. And so Mars cooled down they're hoping it cooled down fast enough that some of the water remained behind this ice. And looks like that's the case. It didn't lose everything. It cooled off so fast that not all the water was vapor. The water was left in terms of ice, so it didn't get blown off. So that was our first encounter where we started to work on planets, was with the Sun and Time program, because it began as really a program in studying the dynamo activity of the Sun, as a function of its rotation, to study that. It wasn't really a program aimed at determining the habitability of planets. So then we were kind of finishing that program, and then we said, oh, let's pick the small stars. So we did the red dwarfs, and it was very hard to get any time or any. We worked with Hubble and X-ray satellites, Chandra, XMM. It's hard to get time then on a program that was looking for doing X-rays or radiation of planets, because people at that time, 2003, 2004, didn't believe the red dwarfs would have enough material left in their circumstellar disk to have planets. So it wasn't until 2005 or 6 that the expert on planet formation, Alan Boss, wrote a paper on that red dwarfs would be perfectly fine and they would form Earths and super Earths, maybe not Jupiters, and that's the case. There's very rarely Jupiter found in these stars, around these stars. So we've been doing that for 10 years, and then we got because of if you want to get warm, and the habitable zone where you can have liquid water around the red dwarf is rather near the star. And in the case of Proxima Centauri, the nearest one, it's 1/20th of the distance that Earth is from the Sun. And when you factor in, when you start to inverse square law of light, it's inverse square law of X-rays and ultraviolet radiation. So on that planet, it's habitable. It's temperate. The temperature's like Earth, but it's receiving 500 times more X-ray emission from its host star than Earth is. And I wonder what that means in terms of whether the planet has life on it or anything, water on it, or has an atmosphere. Because this Proxima Centauri, this is an example of the whole group. Proxima Centauri is 5 billion years old. It's very similar in age to the Sun. And when it was young, because we have models of what it would be like, it wouldn't be 500 times. It would be 50,000 times the radiation levels that the Earth got. And we're not sure. The models, it's very hard to know, what would happen with those kind of radiation levels. But the back of the envelope is more than the back of the envelope. Models starting to indicate that it would lose its water inventories and atmosphere. And the case that you have, what you're hoping for if you're looking for life, is that after the host star spun down a bit and wasn't as magnetically active, that it would be resupplied by bombardment with watery asteroids and comets. Or the other idea is maybe it was further out when it first formed, then migrated in to where it is now. So it avoided the worst times of living near a red dwarf. So there's still still hope, but it's not a big hope that Alpha Centauri has an atmosphere left. There's always these events could have taken place. It could have evolved further out and moved in, or it could have a giant magnetic field bigger than our own that shielded it from the winds and the flares and coronal mass ejections that probably Proxima Centauri is undergoing, and made it suitable for life. And this is the case for most of them. Most red dwarf planets, you have to be very close to the planet to be warm. But it's like it's like living to get warm. You're like a nuclear power plant. You're warm, but then you're getting lots of X-rays and lots of ultraviolet radiation, which it will depend on the planet whether the planet has the conditions to like a magnetosphere to block the winds from encroaching into the planet and stripping it of all of its atmosphere.
Now, what about the Type K stars with their habitability? Now, they seem to fall right in the middle. Are these? Can you envision that this is quite a bit better than the environment around a red dwarf?
Oh, yeah, for sure. We think that we are happy with G stars. The only case of life in the universe is a planet around a G star, and that's us. So there's nothing wrong with having having a habitable planet around a G star. We think, and they just talked about how M stars have problems in all the radiation levels. The only problem we found with the sun, and which is higher mass, is the relatively short lifetime and kind of faster evolution that the sun has than K stars. The sun has a lifetime, main sequence lifetime of about 10 billion years. Red dwarfs are a trillion years, or 100,000 billion years. Very, very long lifetimes. But then you have to deal with the X-ray and UV radiation. What we pointed out is that it's hard to argue with a success story, which is the Earth and complex life. But the evolution, the sun is evolving. The sun is getting brighter, and the Earth is getting very, very close to the inner edge of the habitable zone. So in somewhere about a billion years, 1.5 billion years, or even sooner, with our own greenhouse emissions, we'll have a runaway greenhouse effect. And the Earth will lose its atmosphere first, and then water, and it will probably still have life. This is talking like 1 billion years, 2 billion years in the future, but it would be what you would call extremophiles. So things that, like tardigrades, would be happy, maybe still living on the Earth. So one of the drawbacks with G stars, and is just the faster evolution that it has. They increase in light luminosity about 7% per billion years, which is slow, and we know it gave us time. But our time is running out. With K stars, they're very similar in activity and X-ray and UV measures to G stars, more similar than they are to M stars. So what you're buying with a K star is time. They really much slowly. They have lifetimes of 15 to 45 to 50 million years. And the other thing that is good by planet, when you go to planet searches, G stars are kind of rare. They're like 5% of all stars are G stars, solar type stars, where 13 to 14% are K stars. So you're buying like more numbers for planets to search. And red dwarfs are huge. There's 73% of all stars are red dwarfs. So you're getting like a 2 times more frequent K stars, and you're buying time in terms of nuclear time before the star evolves to become a red giant. We gave a case at the meeting where we had a star that has a nice planet. It's orbiting in, it's about 0.4 AU. This is a K star, 0.4 AU from a K5 star. And everything's nice. It has a temperature tempered like our own. It's getting 25 times more X-ray and 10 times more UV. It's not awful, but it evolves. Like the time it takes for the Earth or the Sun to go from its birth to death, which is 10 billion years, this star only changes 20% in its luminosity. So you would have the whole history of our solar system and Earth taking place in 10 billion years, and a star around this K star, it would only be 20, it would only change, its luminosity would only change 20%. It would have another, 20 billion years or 30 billion years before the star got large enough, more luminous enough to endanger the planet. So that's the case we were making.
That's many, many, many times greater than the star system's lifetime, as far as you said, viability for life. But habitable zones also change. So is it possible that as the sun's luminosity increases over time, is it possible that if we were still here, we could just move further out?
How do we do that?
Well, that's a good question. Well, there was that one paper
on Mars. Yeah, Mars.
Yeah, move to Mars. Yeah. Or there was that one paper that where they speculated that you could migrate Earth over very long periods of time further out.
Yeah, if the sun loses a lot of mass, Earth's orbit would increase a little bit, but that's not viable. The only viable thing that we have 1 billion years, so who knows we'll even be here. Mars would be balmy by that point. But Mars has lost so much of, I'm getting into terraforming. Mars has lost so much of its atmosphere and water that you could never bring it back to Earth-like conditions. that it once had. It once had Earth-like conditions 4 billion years ago. Water, temperature similar, all that, but it's lost something like 70% of its atmosphere, and water maybe 80%. So there's not much left. So even if you heated it up, and the sun would do that, it wouldn't come back to be a purely habitable planet. You could have parts of it that you could live on. You could make domes or go underground, and there you would have water again. Water would run, but it's lost so much that there isn't much to work with. There was a study done a few months ago where that's what the NASA, someone from NASA concluded. We concluded that too, that there is water left. If you want to have colonies, you could mine the water. The water's right under the surface. It's permafrost, but so you could have pieces of it or portions of it that would be habitable, but you couldn't terraform the planet and bring it back to like Earth-like conditions, because it just lost too much material in the 3.5 billion years where it didn't have a magnetic field.
With the K-type stars, could you safely characterize them, as so far as we know right now, could you safely characterize them as better? Is a possibility there that there might be an exoplanet out there around a K-type dwarf that is better and more conducive to life than even this planet?
Yeah, there is. That's the star I was thinking about. And it was discovered, there was more than one. It was discovered by K2, the Kepler mission found it, and it has eclipses, all that. And I think its name is Kepler 442. I hope I remember that right. It's a K5 star. The planet is one of the top 10 planets in terms of closeness to Earth in its properties. It receives about the same amount of starlight as we get from the sun. And it's 0.4, I mean, this is off my head now. This is 0.4 astronomical units from the star. And we think that's a pretty good target. And so it's 9 billion years old. So it could have life on it. If it does, the life would be maybe more advanced than our own life. So that's with G stars, you are stuck that they're only habitable for like 7 to 8 billion years, really, because the star starts to get bigger, and the habitable zone just moves outward. And so this is the one I was thinking about, is that in this case, this star is 9 billion years old, and it's changed. Its luminosity's changed about 20% of what it was when it was younger, and the radiation levels are not that bad. I mean, it's not. It's higher than the Earth gets from the sun, but not off scale like you get with M type stars. Unfortunately, it's pretty far away, but there's going to be a lot. There's a satellite called TESS that's searching for nearby stars, and they have a lot of K stars in their program. They also have a lot of M stars in their program because they're searching for nearby stars. Yeah, we have nothing. There's nothing wrong with the G star, in the case, and they're good. They just don't have as long lifetimes as the K stars. K stars are a little bit more active. You have to be nearer to them to be warm. Like you have to be similar to the Earth. You have to be a half an AU, half the distance that we are from the sun, because they're dimmer stars. They're half the luminosity of our sun. So you do have to get nearer to them, but not on top of them like you do in M stars, to be temperate, to be warm enough to have liquid water. That's what defines the habitable zone. You are right. In our own solar system, Earth is the inner part of the so-called liquid water habitable zone. Is some people have as 0.95, some people have as 0.99. The Earth is on the inner edge of that, and that's because the sun now has increased its luminosity 35% since it was first formed.
Imagine what could be out there, that civilization billions of years old around an orange dwarf. Doctor, we are out of time. Thank you for joining us today, and I hope you'll come back and visit us sometime, and we'll talk more about your work.
Thank you. I had fun. Thank you very much.
While not likely to explode anytime soon, Betelgeuse will someday explode, guaranteed. And while it doesn't pose a threat to Earth, it will be easily visible from here as a very bright blue guest star, much like what Chinese astronomers saw 1,000 years ago. And after that, it will form a nebula, and probably a neutron star. It just goes to show that nothing is forever, even the universe itself and our own planet. Someday there will be no Earth, replaced with a red giant sun, and then a cooling cinder of the sun as a white dwarf, still circled by some of the planets, though in a much changed form. What a dynamic universe in which we live. So quiet around here now that Anna is switched off. I know, right? I can eat any pastry I want. What? Mustache wax? Last time I tried that, I ended up with 2 beards.
John, why are you talking to the opossum?
What? I thought you were switched off.
I just didn't want to interrupt such a deep and meaningful conversation with the opossum. Such wonderful questions, John.
What? No one around here ever takes my side. And on that note, many things happening in the world of astronomy. Next week, I will be joined by Dr. Beatrice Villarol, where we will discuss her recent papers on the idea of mysteriously disappearing stars. See you then.